Well, welcome back. Here we are, chapter 19, where we're going to be discussing chemical thermodynamics, basically the energy in the form of heat of chemical reactions. We talked about this back on 1411 when we talk about enthalpy. So we're going to go deeper into enthalpy. We're also going to explore entropy and the gift free energy and how all that relates to equilibrium. So let's see what we have. So several objectives here. First, the laws of thermodynamics. We will be talking about the second law of thermodynamics and the third law of thermodynamics. The first law is the one that you learned on General Chemistry 1 that says energy cannot be destroyed, energy cannot be created, energy can only be transformed. We also are going to be talking about different things associated with thermodynamics. We're going to talk about spontaneous processes, reversible processes, and irreversible processes, and how this relates when these processes happen at a constant temperature, an isothermal process. With that said, we're going to talk about entropy, which is the tendency of the universe toward disorder, which saves energy. And we're going to see how we can look at entropy at the microscopic level, or even more the microscopic at the molecular level, which is around 10 to the minus 9, 10 to the minus 10. And we're going to see how different molecules, based on their molecular shapes, can have different type of motions, which contributes toward their disorder or their entropy. Once we do that, we are going to go into mathematical calculations, and we're going to see how we can predict if a reaction is going to be spontaneous or not by calculating the change on the entropy of the surroundings. We're going to see how having a delta change on entropy, negative or positive, relates to the different processes. And we're going to see how the free energy or gift free energy can predict if a reaction is spontaneous or not. And we are going to see how temperature will affect that. And then we're going to see how we can link the enthalpy and the entropy to calculate the gift free energy, which is the only one that can truly tell you if something is spontaneous or not. Once we do that, we're going to do that for, we're going to see how we can calculate the entropy by using the values of different substances, just like we did with delta H or enthalpy back on General Chemistry 1. We're also going to do the same thing, same process for the gift-free energy. And then we're going to see how we can calculate the gift-free energy, or delta G, when the conditions are not standard. And at the end, we're going to see how all this relates to equilibrium concepts. So let's begin with establishing the second law of thermodynamics, explaining what a spontaneous process is, and defining entropy. That would be our launching base. So let's start with the problem. Based on your experience since you were born and all the playing you have done, are these things spontaneous or not? A bike going up a hill, does that happen on its own, or do you need to apply energy to it? And the answer would be, based on your experience, no, it doesn't happen on your own. That used to be one of my challenges when I was a teenager, going up a big stiff hill in my neighborhood. So no, that doesn't happen on its own. A meteor falling to Earth due to the force of gravity of our planet, once the meteor is captured by that gravity, it will fall to the Earth. There's no way to stop it. Obtaining hydrogen gas from liquid water, basically taking H2O and break it into oxygen and hydrogen. Does that happen on its own? No, it doesn't happen. If that happened, the ocean wouldn't be around us anymore. A ball rolling down a hill, similar to the meteor, right? Based on the gravity that this planet has, a ball rolling down a hill with nothing obstructing it will happen on its own once it begins to go. So we can say then that this is not spontaneous, spontaneous, not spontaneous, and spontaneous. So you got a pretty good idea what spontaneous means. That's all we're doing here, defining the meaning of the spontaneous word in here. So how can that apply to chemical and physical processes then? Well, before we do, so you can think a little bit more about a spontaneous process, make sure you complete this daily work. Once you do that, then let's take a look at this. Let's make sure that we truly understand spontaneous and that we truly understand entropy with things we know. There's two examples here. A fish tank. One of them contains 4 fish, the other one contains 2. And the question is, which one contains the greater entropy? And the only definition I want you to use at this moment for entropy is the measurement of disorder. So which one of these two systems, the one with 4 fish or the one with 2 fish, have the possibility of showing more disorder? And with a quick process through your mind, you should have said the one with 4 fish. Why? Because those 4 fish can take so many different arrangements. I can have three fish looking to the left when one is looking to the right. On the other one, I can have 1 to the left, 1 to the right. On the 4, I can have 2 to the left, 2 to the right, 3 to the right, 1 to the left, and so many different variations. So the more variations you have, the more disorder the system can express. We're going to call these particular variations, it's like a snapshot every microsecond. We're going to call this, we're going to relate this to what we call microstates. So the more microstates you have, the more entropy a system has, the more disorder it has. So keep that definition and analogy in mind. So first law of thermodynamics, quick review. Energy cannot be created or destroyed. It can only be transformed. The total energy of the universe is constant. From the moment the universe began, however it began, the energy that the universe had from that moment is still the same energy we have today. We haven't gained, we haven't lost any. It only has been transformed. Energy can, however, be converted from one form of energy and transferred on the system from the surrounding to vice versa. And the best way to express energy is by saying that energy is a combination of heat and work. And work is nothing more than what happens when a force is applied and causes a displacement or a change in position, a change in volume. That's what we can say, that work equals pressure change in volume. So that would be a way to define work. Pressure is a force, a change in volume is a displacement, so we can say that P delta V is work. But in general, and this is something you learn in General Chemistry 1, energy is a combination of the heat of the system and the work that is done on the system or performed by the system. And that's just the first law of thermodynamics, which, like I said, we discussed on General Chemistry 1. The one that is new to you is the second law of thermodynamics, that tells you the entropy of the universe increases in any spontaneous process. So whenever you can say, ooh, I have more disorder now, that means that the entropy increase. So whenever you have an increase on entropy, that means the process that you're observing is a spontaneous process. And we're talking about the entropy of the universe, which is a combination of the entropy of the system, what you are observing, plus the entropy of the surrounding. And remember that you already know that whenever the temperature increases, particles will move faster, and that increases the kinetic energy. And if you increase the kinetic energy or something, they can move faster, so they can have a lot more different positions in a given time. So you can have more microstates. So increasing uh, the heat or the energy of a system is going to increase the entropy by default. And these are some of the formulas that we can use to define entropy in relation to enthalpy. And remember, enthalpy is the thermal energy of the system. It's the heat absorbed by a system. And a system is whatever you are observing. If I'm looking at my food right now, that's the system. Everything else, my living room, my sofa, and everything else is the surrounding. Those two combined is the universe. So we know that if we measure heat at a constant pressure, then that would be the same as the enthalpy. So as long as we don't change the pressure, because remember, energy equals Q plus W, and W equals pressure times change in volume, right? So as long as we don't change the pressure, the energy is basically going to be just the heat. So as long as we measure heat at a constant pressure, that's going to be the same as enthalpy. And you learn on Chem 1 that measuring heat is really easy. You just need to measure the mass, the change in temperature, and be aware of the specific heat of whatever substance you're looking at. So if you can measure the heat at constant pressure in the lab, you're actually measuring the enthalpy. So remember that. And you already know that entropy is a measure of disorder or the randomness of a system. And we tend to measure the change of enthalpy. And the only way you can determine if something is spontaneous or not is by measuring the delta G, or the free Gibbs energy. And if this is less than zero, the process is spontaneous. So by measuring enthalpy, that we can calculate by going to the lab and measuring mass, change in temperature, and using the specific heat of that substance, and by knowing the temperature and the entropy, you can calculate delta G, or Gibbs free energy. And if that happens to be negative, then you know the system is the process is a spontaneous process. And you can predict, yeah, that reaction will happen. It's going to be a spontaneous reaction. So instead of wasting hours and hours on the lab trying to run a reaction, you can calculate it first and then determine, yes, that's a viable reaction. So spontaneity can be affected by different factors. So some different factors can affect how spontaneous a system is. And temperature is a classic example. So for example, if I take ice at any temperature above 0 degrees Celsius on this planet, at 1 atmosphere of pressure, any temperature over 0 degrees Celsius, the ice will spontaneously become a liquid. If I take water and I put it under any temperature below 0 degrees on this planet at 1 atmosphere of pressure, immediately you can expect the water to freeze. So those are spontaneous processes. Once you are at a given temperature, you know what's going to happen because you've seen it before. It's a spontaneous process. So that's a spontaneous process. Freezing or melting, those spontaneous processes are affected by temperature, obviously. They only happen above or below 0 degrees. So spontaneity can be affected by different factors. One of them is temperature. So it could be spontaneous at some condition, but non-spontaneous at other conditions. So let's talk about more about the entropy of the system or the disorder. Because remember, if if we can define if we can define the entropy, so if we can define the entropy, right, then we can combine it with the enthalpy, and eventually I can tell you if the system is spontaneous or not. Delta G is the only one that tells you for sure that a system is spontaneous. So let's look at these problems to see how to better understand the tendency of entropy. So without doing any calculations, we're just going to be using what we know, the concept we know. We're going to predict the sign of delta S of the system. Delta S of the system in the universe tends to be bigger than zero or positive. So what do we see on this reaction? On this reaction, we see two formula units that are solid, and it's producing two more formula units that are solid and three molecules that are gas. So it went from 2 fish to 5 fish. Remember the analogy we saw at the beginning? So which one you think is going to have more randomness? The one with only 2 particles or the one with 5 different particles? In addition to that, three of them are a gas. So those gas particles are going to be moving faster, which even brings in more randomness. So based on that, since we know the universe tends toward disorder, we can say that the sign of this is going to be positive, bigger than zero. On the next one, we have two molecules combining into one molecule. Two molecules is going to be more randomness than only one molecule. So that's going to decrease the disorder, the randomness, the entropy. So that's going to be less than zero. On the next one, we have two atoms of sodium, one molecule of chlorine combining to give us two molecules of the solid. So we used to have one that was a gas with a lot of kinetic energy. The gas is gone, so it became more organized. So this will be negative also. And on the next one, we have one molecule of nitrogen, three molecules of water, making two molecules of ammonia. So we're going from 4 to 2, so it's becoming more organized, so the entropy is going to be negative. So becoming more disorganized, that's an increase in entropy, and we say that's going to be positive entropy. Becoming more organized, that's a decrease of disorder or decrease of entropy, and we're going to say that that's going to be a negative entropy. So that's how we can predict the symbol of the change of entropy of the system. So we're not defining entropy, we're defining the change in entropy of the system. So with that said, go ahead and do this daily work and make sure you explain why you're saying that the same way I did. And with that, we can say that we talk about the second law of thermodynamics, that entropy of the universe tends toward randomness, toward a positive value. We understand better what a spontaneous process is. We also know we are kind of ahead of ourselves, but we also know that spontaneity can only be defined by the gift-free energy, which is given by the change in enthalpy combined with the change of entropy times the temperature of the system. And we saw also how the uh, change in enthalpy is nothing more than the heat measured at constant pressure divided by the temperature. And then we talk about entropy, and we saw how entropy is a measurement of the disorder, and the universe on any spontaneous process is going to tend toward entropy to be positive in general. But remember, spontaneity is only determined by the gift-free energy for sure. And with that said, we're done with the first section. So very soon you should be seeing the second section where we're going to go deeper into the measurements of entropy.